I would like to focus on the title toward an end-to-end visual perception system for navigation in human environment. As you can see, it's mainly about how we can develop an end-to-end visual perception system when there is a dynamic environment, like if there is a human, and how we can have a perception system where from the robot sensor can understand human behavior. Okay, before we start the presentation, I need to a bit discuss about the motivation we have. There are many applications out there, and the goal is to have an autonomous agent like a social robots or even autonomous car to move in the environment, which is the dynamic object is there. It doesn't. It means there is not only the environment, which is a static, but also there is a dynamic environment around the robot, which mainly we focus on about when there is human around the robot. And it is very, very important if there is a robot which needs to be in a human environment to try to, before doing any task, to have a high level understanding of the human around it. It's what's a behavior, what's the action, the human around that, and try to, if the task is, for example, to navigate through, it's a very important to be able to predict a complex behavior of the human. Usually we have a robot which is equipped with the multimodal sensors, which could be very different sensors. The robot can be only equipped with the cameras. Some robots and also some most of the autonomous driving cars is equipped with lidars. You might have the other sensor like IMU, GPS, and you might provide some kind of mapping for the robot in order to navigate from a static environment. But it's much more easier if there is no any dynamic environment, dynamic object in the environment for the robot to navigate. When there is a dynamic, then that would be a bit more complex task to do. Means the robot should be able to detect the dynamic object like human, track them, and then do a high-level reasoning about their behavior and action. And actually, before we a bit discuss there is a lot of research out there which try to have a robotic application, and then the planning is done directly from the sensors with learning a model, for example, a neural network trained using label data or reinforcement learning to do the planning task. With all respect, which might be applicable and useful in the environment which does not have any dynamic object. But when we have cars, when we have bicycles, when we have a moving object around the robot, when we have a specifically human with the very complex and unpredictable behavior, is very important for the robot to have have a kind of the understanding from the people around that. Without we cannot really simply use the end-to-end learning with no perception module in the between and try to navigate in the human environment. This argument can be controversial, but I just need to a bit more explain why we need perception for the robotic task. I believe end-to-end learning is the way to go. Means we need to have the end-to-end system because the end-to-end system is less engineering involved. There is no any handcrafted rules, and then we don't need to propagate the noise from one module to another module. We have, but end-to-end learning with a perception module look like we are assuming human visual system. There is no brain involved, and then directly from the eye, what we see is directly go to our our muscles, and then we plan. And then, okay, yes, we can possibly do such a that training, but we don't expect really to have a very smooth and reasonable behavior in emotion. From the biological perspective, actually, human brain is much more complex. Our visual system very complex. We have a different level of the perception, visual perception, in the different part of the brain. And then when we have a high level knowledge about what we see, then we have like a part of the brain responsible for our motion, and that's how it's communicated. But far from the biological perspective of this problem, if we don't have actually a perception when we try to do planning, when we do end-to-end learning, one of the things is that we don't know really how the model is generalized for the new environment. We are really too much relying on the loss of training data and look at it as a black box to train a model to be able to do the planning with the hope of it's generalizable enough, and our key to collect more data. Okay, is it scalable? Is it tractable? All is questionable. And plus, okay, at the end, we don't know how generalizable is the what we learn actually. And it's hard to interpret. And if there is a fault or accident happen, we don't know exactly what's going wrong. Okay, so if we know the robot from the sensor directly do an action, end up to have an accident for an autonomous robot, then how we debug this system? That's a main problem. And this is a kind of thing is not only discussed in my presentation, it's also different people looking into that. Means end-to-end learning is good, but because we don't know how to do with perception, that doesn't mean we should skip the perception module. And specifically, we have lots of good perception and all end-to-end trainable when we don't have a moving object. It means like we can have a understanding from the 3D environment. We can train a model to build this 3D environment, find the obstacle, do even semantic semantic perception when there is no moving objects. When there is a moving object, there is other perception which make it a bit much harder. At least we don't know lots of components how to make it end to end. And then one of the target of the my team in Stanford and Monash here now is to build such a system to be able to, for example, understand human behavior directly from the sensors to high level knowledge about the human behavior, human action, social interaction. So as I said, I'm not gonna go toward every possible perception we can have for the robot. I mainly focus on the perception task for understanding and anticipation of human intention and social activity. And we just try to say, okay, what kind of like a task we require and in which levels, means that we design a multi-level, multi-task system to be able for the robot from its camera or other sensor to fully understand human behavior. And that would be the topic of my talk. I'll go through some of the works we actually we've done in the past and currently we are doing to deal with this end-to-end perception. It's a very important. Some of those or maybe the most of them is already exists. It means there is a lots of paper out there in the vision and robotic community to try to solve the similar problem, but they are mainly look at in the sub problem. Input and output of them is simplified. It's not a practical or the most of them also followed by the methodology followed by post-processing stop us from using them directly into the end-to-end learning. So it's a very important if we want to have from robot to planning and we want to have all of the perception in the middle, all of the component to be end-to-end trainable, and it doesn't really be followed by a post-heuristics. And therefore, those perception tasks can be compatible with the end-to-end training scheme, right? Okay, we start from like a basic level. I might change it to the basic level. Low level is the wrong terminology. Basic level tasks like a human detection and how and general object detection. This seems to be very trivial, and we know how to solve this problem. But I kind of disagree in the sense of we have a good object detection, but they are not yet, at least up to now, was not end-to-end. Let me a bit clarify on this. Okay, the people who are familiar with the object detectors, they know like we mainly have a three generation of the object detectors, and which is either RCNN-based detector, SSD-based, or YOLO-based detectors. Means that everything is out there, most of them is the variation of those, like is a single shot detector like a SSD YOLO and then rating on it, or is a two-stage like a faster RCNN based. Independent from the which methodology we pick and for formulating the object detector, all of them has a similar problem. Let a bit clarify on that. Means we have a neural network, like a convolutional neural network, which input the image, and independent, there are the two-stage or single stage. What they try to generate in the output is almost for a coarse level of the every location and scale. We try to estimate a bounding box, actually. Not the bounding box, if that location and scale include the object or not. Means we try to model a problem to a more classification in order to find out if there is an object or not, then if it's the object, then what category it is. But is mainly you are going to like every 10 pixel and a coarse level of a scale in order to find out if that's contain an object or not. And then you have definitely a regression loss for them to try to make the box more closer to mean you actually adjust this coarse level to more fine-tuned estimation. But ignore the regression part, which is just fine-tuning this grid, actually, which we call anchor boxes, or we try to learn a score for each of them to be object or not. But is it the final output? No, actually, there is an inevitable process. It's called the non-maximum suppression. I don't know how much you know about that, but this part is a heuristic and it's not a part of learning. The idea in NMS is to say like is a discretization process, because we need to, from this dense grid, we need to just pick a subset of the boxes as a final output. And we cannot simply threshold them. And we just need to do a more complex optimization, is like a pairwise optimization. And non-maximum suppression is simply look at every box you predicted with the score, go to the local area, find the box with the highest confidence, and suppress any boxes which has a more than some certain threshold. So in that way, if you have a multiple box on the same person, you pick the highest and then suppress the rest. Okay, there is two things here. One is that the performance of this detector is hindered by that. Means we have a neural network, like a convolutional neural network, which input the image, and independent, there are the two-stage or single stage. What they try to generate in the output is almost for a coarse level of the every location and scale. We try to estimate a bounding box, actually. Not the bounding box, if that location and scale include the object or not. Means we try to model a problem to a more classification in order to find out if there is an object or not, then if it's the object, then what category it is. But is mainly you are going to like every 10 pixel and a coarse level of a scale in order to find out if that's contain an object or not. And then you have definitely a regression loss for them to try to make the the box more closer to means you actually adjust the discourse level to more fine-tuned estimation. But ignore the regression part, which is just fine-tuning. This grid, actually, which we call anchor boxes, or we try to learn a score for each of them to be object or not. But is it the final output? No, actually, there is an inevitable process. It's called the non-estimate a bounding box, actually. Not the bounding box. If that location and scale include the object or not, means we try to model a problem to a more classification in order to find out if there is an object or not. Then if it's an object, then what category it is. But is mainly you are going to like every 10 pixel and a coarse level of a scale in order to find out if that's contain an object or not. And then you have definitely a regression loss for them to try to make the box more closer to means you actually adjust the discourse level to more fine-tuned estimation. But ignore the regression part, which is just fine-tuning. This grid, actually, which we call anchor boxes, or we try to learn a score for each of them to be object or not. But is it the final output? No, actually, there is an inevitable process. It's called the non-maximum suppression. I don't know how much you know about that, but this part is a heuristic and it's not a part of learning. The idea in NMS is to say is a discretization process, because we need to, from this dense grid, we need to just pick a subset of the boxes as a final output. And we cannot simply threshold them. And we just need to do a more complex optimization, is like a pairwise optimization. And non-maximum suppression is simply look at every box you predicted with the score, go to the local area, find the box with the highest confidence, and suppress any boxes which has a more than some certain threshold. So in that way, if you have a multiple box on the same person, you pick the highest and then suppress the rest. Okay, there is two things here. One is that the performance of this detector is hindered by this post-processing, which is not part of learning. And another thing is that this post-processing cannot be avoided, and therefore those detector is not really can be easily incorporated into the end-to-end learning pipelines, unless we just rely on the self scores and these dense measurement, which is like a less desirable for the later stage. As I said, another problem is this post-heuristic, independent how we do the learning, is kind of like become bottleneck for object detection, which is very, very important for the task of the navigation. When there is like an area which there is a lots of people, visually we can see the human, but we kind of this post-processing suppress the boxes relevant to the people partially occluded. Let's clarify a bit more. What we see usually as the output of the deep neural network coming from this type of object detector is a dense proposal of the boxes, and some of them is the threshold to get some subset of the good boxes, and then that subset given to the as I said, is that heuristic to generate final boxes. What is really happening is as I said, this idea for the non-maximum suppression is to pick the box with the highest confidence and to suppress everything which has a more than a certain threshold. Means, for example, pick this box and then suppress this one, pick this box and suppress. You can see this crowded area, then you need to pick and suppress the rest. And this is what you get. And what you really lose, if the two boxes, which here is represent two humans, which is visible, even your backbone, which your training scheme was really successful to predict this 100% there is a human here. But because you have this post-process and say suppress okay, pick the like some box and everything has a more than certain threshold with that, suppress that one, then you need to suppress that one independent from what is the score. Make sense? And this part, independent from the overlap value you pick, you cannot really have any threshold which you can ensure you can detect really partially occluded person or object in the high dense crowded area, and while you don't get the multiple recall on the isolated person. So I'm not gonna explain more than that. If you are interested, there's a lots of research. We already discussed this. NMS, it's a bottleneck for the object detectors, and then we are not able really to see to detect like a people in the very cluttered area, and that's a very high risk for navigation tasks, because like there is enough visual to learn if the multiple boxes include one object or more than one object. If it's a one object, then try to suppress it, and if it's not, then try to keep as many as the box. And those approaches, assuming that every relationship is a pairwise relationship, and you add a new very expensive neural network on top of the detectors to deal with this hypothetically wrong formulation for object detection. So you are at a pairwise model, and which makes the detector far from being real time, which is another thing we like about the YOLO, for example, to be a single stage real time. We don't want to really add another network. We make it like a 2 second or 3 second to just process. And we try to save a bottleneck, and then we add lots of computation. Perhaps we could see the object detection as another way, different from what is formulated currently. And in around the 2017 and 18, I started to work on the topic which called how we can have input and output sets from the neural network. And what is sets, just make it clear, sets is a collection of elements which are orderless, means doesn't have is a permutation invariant, and the sets can be different in size. So what we know we can do with the existing neural network, like a CNN and even like a RNN, with the CNN we can input a tensor and output a tensor, like we can input the image and output a vector or n-dimensional array. With the RNN, we can have the input and output sequence of those tensor to tensors. But what we want really to have the output which does not have any order. And I start to work on how we can predict sets using feed-forward neural network, and I was quite pioneer on that topic. But one of the main reason I work on this topic was the many potential application. One of them was to say, look, object detection is not formulated correctly. Actually, if we want to have a model, input to that model is let's say is an image, but we want to, in the output, predicts directly a set of bounding boxes. Is a set of boxes, or set of the coordinate of the boxes, which does not have any order and is not in the fixed size. One image contain no object, one image can contain 100 objects. So how we can have a neural network which can predict sets, and if we have that one, we can reformulate object detection, and we don't need any post-heuristic. It's an end-to-end training. And I'm not gonna go into the detail of that, but we successfully could show we can have a net for deep neural network with the existing backbone, with the very subtle manipulation, which we can generate sets, and we can reformulate object detection as a set prediction problem. And we start to compare it with the faster RCN and YOLO, and with the same backbone, very identical, with the very similar training scheme, all of the parameters optimized for those faster RCN and YOLO. Actually, we have a YOLO v3. And we have like an R detector, which is the same backbone, which just different formulation to predict sets. And we could like outperform them, not in the case if there is an isolated target. Means if there is an isolated person, we can very well, every method can detect it. But the problem start to, we become superior if we have the cases we have like this white lady and or another person behind this man with the blue shirt and white short. They because of non-maximum suppression, they need to suppress that one. Means independent from how good was the proposal score is. And because of this new formulation, which doesn't need a non-maximum suppression, we are able to detect. And that's has a two advantage. We can improve the performance, is a single stage, very fast, and is end-to-end. But that time we just tried on the small scale training the set network. It was a bit harder to than the conventional deep learning modules. We didn't make it really large scale object detectors. Another work I've done for object detection, which is not quite related to the end-to-end learning, but is more about the a simple idea about how we can have a better regression losses for object detection. That's a very important for the localization of the box in the right place. Again, is very important for the task of the navigation tracking, to have like the box to be the place very in the right position. Just to clarify, the idea is super simple, and we try to, in the paper we published in the CVPR, which is a very popular paper, we try to say like usually the way we define the loss for object detection, independent is a 2D and 3D. We have a parameter representation from the box, for example, center of the box, width and height, and or two corner representation, let's say, and we try to minimize some like a norm between the truth value and predicted value in the respect to that parameter representation. Okay, definitely parameter representation matters and the norm matters, but it's a really we can really easily show independent from the parameter representation and then what norm we use. If we have a metric which is like a intersection over union, then the surrogate loss we use for minimization may have not really a strong correlation with the R metrics. Means I hope like you are familiar with the intersection over union. It's an intersection over union between two shapes, like two bounding boxes. That's a metric we use to measure the proximity of the prediction to the truth. And this intersection over union has some property like is a scale invariant. And but you can show independent from the parameter representation you pick and norm you pick, that won't be a scale invariant. So you have like a discrepancy between your losses and your metrics. And in the left-hand side, we just showed like provide one of the example. If you want to know more about that, but it's you can find it in the paper. Let's assume, for example, green boxes is the truth, and we have a 3 set of prediction, and the prediction is formulated as a two corner representation. Means two corner of the box. We try to make it close to the 2 corner of the truth. And we use like L2 norm, for example. It's a really for simplicity, let's assume the corner of all of these three boxes, one of the corner is fixed. The other corner can actually turn around a big circle, which has a constant distance to that second corner. You can show independent from the any prediction, which is which is located the other corner located in the one of the the other corner located in the circle has exactly the same distance to this corner. So therefore, your loss would be identical for all of these three. But if you measure the intersection over union, that would be significantly different. So that was our motivation to say it's a very important to understand what's our metric and what's our loss. And then we show in that paper, we can directly use intersection over union for two-axis aligned bounding boxes as a loss. But it has some problem, which we try to generalize it. And the idea for the generalized intersection over union was we want to have same thing as the intersection over union, but intersection over union, if two shape does not overlap, it doesn't have any understanding of their proximity and the shape similarity. Means if an A and B just touch each other and B is exactly similar to A, independent from is not or it is intersection over union is always zero. And what we actually try to say, can we deal with the problem of the intersection over union if two shapes does not overlap? Can we have still some notation of visual similarity and spatial proximity without handcrafting it? Means, can we have a similar concept of the intersection over union to be a scale invariant, to be metric, but we just generalize it? And the idea is super simple, and this is we come up with the dealing with the intersection over union as a metric and also later as a loss. Does not have any value when there is no overlap, then how we can address when this problem? And the idea is to say, if we have a two convex shape, we try to find the tightest convex shape between these two shapes, which you can see obviously this. If you really have the tightest convex shape between is a part of B and this dashed line and this part of A, which makes the tightest shape between that. We notify that shape as a C. And in the generalized intersection over union is maximizing the intersection over union while minimizing the empty area, which is the C excluding union of A and B divided by the normalized value of C. This we try to minimize. It means if two shapes actually become closer and closer to each other, this empty area becomes smaller and smaller. If the two shape overlay, that's this value completely wash away. And that was a really easy extension to the intersection over union. But we later show that if we have two bounding boxes, we can have an analytical way to calculate intersection over union and generalized intersection over union. We can show that all of the this actually component which we need to from the bounding box calculate intersection over union to and in generalized intersection over union has well-behaved derivatives. Therefore, you can directly use IU and GIU in that case as a loss, and then loss and metric become very similar. Again, sorry, I cannot really go more deeper into that. If you are interested, it's a very, very simple idea. I call it high school idea in that sense. Everyone can follow materials, but it's a very easy and very effective. To this end, most of the state-of-the-art object detector are now using the IU and GIU losses in there, and they get their a boost performance with just changing the regression losses, including the new faster Mascarsian and YOLO V3, which we already provide the code for that. There is other very popular detectors called fully convolutional one-stage object detection, published ICCV last year, FCOS. That's someone later incorporated the GI loss, and the performance improved significantly. And there is one paper appear in this year's ECCV. I think the presentation is tomorrow or the day after, I'm not sure. And that one is really interesting because it's inspired by our formulation for set detector. Say the detection should be modeled as a set prediction, and they use also our losses, and they had the transformers, and they try to show these three together. You can have an end-to-end multi-object detector, which has a superior performance on YOLO, fast RCN, and other state-of-the-art object detectors and mask generators on COCO datasets. And as I said, this formulation, because the set prediction doesn't need non-maximum suppression, they can deal with the partial occlusion. IUGI also extended for 3D cases, and there is a couple of papers appear in the literature for that. If you are interested, you can have a look. All right. Now we have, actually, we can have with the similar things like a set prediction, better losses, we can have a better detectors. Not the better detectors, I mean end-to-end object detection with no post-processing or heuristic, like a non-maximum suppression. But one of the main problem we have in perception module we want to develop for dynamic objects is we are not sure how to make the multi-object tracking end-to-end. There is a lots of claim out there in the literature. People claim we have an end-to-end object tracking. And at the end of the day, if you just very careful look at them, they have they are actually detection plus some matching heads. And the matching heads is just try to make the things should be matched based on 2-frame or multi-frame to be closer to each other. And you actually model the tracking as a detection plus 2-frame matching. And that's not a really end-to-end, because you need to still do the final decision by hard decision, and then they are relying still on the Hungarian to match, or some other optimization like a network flow to create the matching, and still initiation, termination, and occlusion handling is like just a bunch of heuristic. None of the components is learnable actually, and we as I said, we have a bit of claim about the end-to-end multi-object tracking, but none of them is all, and that could be potentially one of the problem. What we did so far for end-to-end multi-object tracking, I'll go through like two of the paper which my team work on, and one of them is a III, which we try to do formulate multi-object tracking as a truly end-to-end learning. I'll try to explain it, but still there is a way to go. It means still problem is not quite solved. The first paper is we actually is about how we can do the real-time 3D multi-object tracking, and we published this paper. Will appear in the IRS this year. This paper is about how we can just fuse multimodal sensors and how we can use both RGB and the 3D LiDAR data for tracking multiple human. Again, this paper is not really end-to-end. Still, we are relying on the matching algorithm like JPDA, and we rely on Kalman filtering and the other heuristic to generate the tracks and for initiation termination. But the goal of this paper was to how we can have the state-of-the-art approaches in 2D and 3D in LiDAR, and then how we can blend them to both do a better detection and to do better matching actually in the 2D, 3D, and then how we can leverage this both sensor modality. And if I just skip this part, the main idea behind that is to say, we have a detector, we try to train it, all of the components trained together. we have a detector, 2D detector, try to detect the 2D objects, and then we have extract the 2D appearance model from that as a 2D feature. Then 2D boxes is used to create a frustum. I apologize for that. Yep. A 2D bounding box is used to generate a 3D frustum, and the 3D frustum try to segment the point cloud and generate the 3D detection. The idea is exactly the same as the F-point net, but then when we have these 3D bots, we have a point cloud, and then we can create a 3D feature or 3D point cloud feature. And then we have a 2D feature and 3D feature, how we can blend these two to generate a final, how we can learn to generate a final scoring for the tracks to see if that's similar to the detected object or not. But at the end of the day, sorry, there is a problem. I need to restart the program. I apologize for that. There is a problem with this video. I apologize for that. I just need to pause the video. Sorry, I apologize for the problem. Obviously, I have a bit of problem with this video. Okay, I think this time should be okay. But in the tracker part, when we have this 3D and 2D detection, which this 3D, 2D is associated, and then this matching information, which all come from the deep learning, still we rely on the association technique like a JPD, and we have a filtering, multimodal filtering. In this work, we mainly try to have a real-time framework which is working, and the goal was not really to use the state of the goal was to use the state-of-the-art approaches for using point cloud and images. But the problem is definitely it performed very well, but it's not yet end-to-end because we rely on the Kalman filtering and like a data association technique plus heuristic. And we conducted some actually experiment on the robot itself directly when the robot run between human in order to evaluate how would work this 3D tracking in the when its algorithm run on the robot itself, and you can see is the some visualization of what we generated. The number above the person represent the IDs. And it shows we have a few just ID switches and single mistrack across about the 2 minutes of the data, which is quite reasonable. Means we are able to reliably do the 3D tracking of the human directly from the robot platform. But as I mentioned, the main problem we have actually is this is not the really truly end-to-end multi-object tracker. In order to have a entire of the system to be end-to-end, we need to deal with this and work towards some idea to make this part also end-to-end. There is a paper we published on 2017, which can be still the only paper which is truly end-to-end multi-object tracking. It has its own cons and pros, but there is no real any heuristic use in this pipeline. The idea was on the time which like there was not many of this deep learning module available, was quite good and interesting, and the paper is quite popular as well between the tracking community. But no one really could follow it due to the some but again, the same problem of it cannot be scaled for the large object. But the idea was interesting because we just rely on the Bayesian, and we had the inspiration by Bayesian learning. Like in the Bayesian framework, we have a prediction. Try to learn the dynamic of the, try to use some posterior to predict the posterior of the dynamic object. When we have a measurement, then there is an update. And we have usually a data association module. But how we can have all of the components we want, instead of being model-based, to be model-free, and we use some RNN and LSTM to deal with that. The idea was we could really use the RNN for each target. This RNN is shared between all of the target, assuming we know we want to track n target in a video, like 100 target. You can just decide about the maximum number of target. And then how we can have the input to those RNN module, what we see before and what is the measurement, in order to predict the state of each target. So can we learn RNN to learn the motion model of the target, and if there is a measurement comes to do it update? Yes, definitely we can do that. But the problem is not as easy as just rely on the RNN to predict and update, because we have lots of detection, and the detection, some of them is due to target, some of them is false detection. We don't know which measurement belong to which target. That's why we have the data association part. And we try to learn data association by a set of LSTM, which that iteration over the LSTM represent the data association over target. So we have the time in the x-axis, and the y, which is the depth which we solve, is the data association. Again, a bit clarified. We have an RNN module which we try to learn by inputting the previous state of the target and learn to predict the next state of the target without seeing any measurement, like a motion model. Learn to predict how the target moves. And then when H here is the hidden memory of the RNN. And then if you have a set of measurement, all measurement we receive, if we know the data association as a soft matrix, means can come from any process, which I explained how we learned that a matrix. Then we can generate a updated state of the target. And in order to deal with the initiation and termination, learn to do initiation termination, we rely on a binary variable to say if the target is alive in this frame or not. If it's not, and not the start, that means target is not initiated. And if the target exists before but not this binary variables is 0, means it's terminated. So we rely on this binary indicator actually to predict if the target is learned to predict it, initiation and termination. As you can see, sorry again. As you can see, we try to learn motion model, update, and if the target birth and death phenomena end to end. The only things we don't learn in this module RNN for each target is the data association, and I will explain it shortly also how we do that. So the output of this RNN module is the predicted state, updated state, and then binary indicator if the target is alive or not. We have another indicator, which is simply a subtraction of these two binary, means previous time frame and the current time frame. And the reason we use it is to kind of use it during the training module to force, if the target was alive, it's not immediately due to misdetection, this value move to the very small value, make more smoothness in the predicting these binary variables. So the loss we use for training this RNN, it has a prediction. X tilde here is a ground truth. We try to make the prediction truths close to the ground truths, update close to the ground truths. And then we have this binary variable, which is simply a binary cross entropy. If the target is alive from the truths we know, then we try to make these binary variables like close to the 1. During the test time, we just rely on what is predicted to be a target alive or not. It means we threshold it if it's above 0.5, target alive, otherwise it's not. And we have that smoothness. We try to say, when we want to minimize, say the difference between these two should be minimized. Means we don't like suddenly 0 change to 1 and 1 to 0. And the reason we do is, if we have a tracks, which we have a set of misdetection in between, and target is alive, if we don't have this smoothness, as soon as a misdetection happens, it has a tendency to predict, because it's really hard to find out the difference between occlusion and termination. This like a variable have a tendency to drop below some threshold. But if we have this smoothness, we can have a better behavior for the target, a smoother behavior before being terminated. So this is how we can learn dynamic prediction, update, and birth and death for each target. But when we have a multi-detection and multi-targets, then we have to learn a data association. And the idea for the data association also, the input to this is the pairwise matrix between all of the predicted X star, which is the predicted position of the target in the next step, and the measurement at time. We try to calculate the pairwise distance between all of the state of all target and all of the detection. And this is like a matrix. And every iteration of LSTM try to predict a distribution over which detection is more likely to be like affect this target. And then we try to train this module using like a simple softmax. And the ground truth of that could be anything coming from Hungarian, for example, we try to learn Hungarian by doing the LSTM, or any other data association. So we can, and the output of that, it would be a vector for index of I for each target. So if you have a n target, we have n iteration of LSTM to predict. And as I said, this would be like a deal with all of the things happening in the multi-target tracking, or like a long-term learning of initiation and termination by relying on the recurrent modules, and then also learn data association and the motion and measurement of the update module of the how to update the state from the measurement. It's a very nicely formulated, but there is some some cons and pros about the technique, which is not make it yet quite practical for larger scale multi-object tracking. For example, the data association model sequentially, and it needs some truths, which we rely on another method like a Hungarian to generate that. But that would be still the only methodology which rely like a model the problem end to end. We are working toward, my group is working toward a new version of that, which doesn't have the most of the problem which this method have. We hope that can be a scale up, and we can have a truly end-to-end multi-object tracking. Okay, assuming we have like this basic level end-to-end, like a detection, we can have the tracking. Still, as I said, there is much to go on that part in multi-object tracking. But for the navigation task, we care not only about tracking the object, but also estimate their immediate future, and that's a very important for the action and planning. And one of the popular topics recently is how we can predict the future of the moving agent, like cars or even specifically humans, given the past history of their tracks. It means how we can predict their future, and how we can train a model to do that. At the first glance, this problem seems to be very trivial. We can just use the RNN to encode the past history, and then use the RNN to predict the future. But the problem is not as easy as because the behavior of the moving object and the human is influenced with by the environment, by the obstacle in the environment, specifically with the other human in the environment. Means if I move in the corridor, which there is one person behind me just following me, and there is one person coming toward me, actually my trajectory means can be influenced by the person coming toward me. I need to just change and deviate from my route in order to not have a collision. So if you have a bunch of the target, which target affected which target, and what is it? That's what it's known as a social trajectory forecasting. Means in the considering this problem is the quite old problem in the robotic community, and people try to learn try to model the social behavior, but there was a model base, and we don't know what is exactly the human social behavior. So later on, the community tried to learn this interaction between the target by deep learning. And very first paper maybe tried to solve this problem was a paper from my colleague Alex Allahi, which is another popular paper. It's called Social LSTM, which try to say if we have a bunch of LSTM, how we can create a joint representation between target before decode and predict the future of each target. And also another thing is very important in this topic is about the physical environment. Again, obstacle, it matters for us, how we plan our future. Means we cannot really hit the wall if there is a wall behind me. So that's very important to be modeled in the like a learning scheme. So we had a paper, it's called Sophie, published last year, and the paper is about given a map, which can be a top view map or an image, direct image from egocentric view of the robots, and then given them like a track target so far, how we can predict their futures, and how we can learn a joint representation between them. The idea for the joint representation is very easy. We rely on LSTM to encode the past history of all of the targets. Then we have a module we try to learn a joint feature representation between target, but that module should be insensitive to the order. Because it doesn't matter in which order you input the LSTM and tracks into the LSTM. At the end, the feature of the X target should not be sensitive to the order we created. So therefore, it's very important to input with the permutation variant function. Social LSTM use the max pooling in order to generate the joint representation. In this paper, we try to rely on actually sort function to generate a joint representation between the tracks. For the physical objects, we try to encode the feature with the CNN. Main important part of the novelty of the paper is to say not every agent affects the other agents equally. So for predicting these agents, it's very important to know which other agent or person affect its future. And then we rely on something we call it social attention, which try to find the attention between this trajectory in order to weight which attention is more important. Similarly, we have a physical attention in order to say like a given image or like a top view image, which part of image is important for this agent. And having these features, which have including the attention of the social interaction and the physical attention, then we have a feature representation. Then we give it this feature, which is like a to each LSTM generator to generate the future of each agent. Actually, if we look at the generator means prediction problem, you can look at it as a generative model. So you can have when you generate a model, you can have a discriminator to just try to improve the performance of the generator by put them in the min max or competition with the generator. And discriminator, if discriminator find out is a predicted value, then you generator needs to improve its output. Similar concept can be used for the trajectory forecasting, in the sense of like we can predict the future of the target while we'll use LSTM as a discriminator to say what is generated is a fake or is from the real truth. So we have the GAN module similar to the social GAN previously published as well. So this model try to, given the trajectory and then some image or map, try to predict the future trajectory of each agent, and because it's the GAN, it gives the distribution. But the previous model had some problem. For example, model the interaction between target with the handcrafted distance between target, and then sort them accordingly, and then use some attention. And another thing is they use the typical GAN, which can just model a single modal distribution. Later on, we had a paper in NIPS last year where we tried to do the two main actually contribution. One is the interaction between tracks can be formulated as a graph, and then we can use the graph attention modules actually to learn interaction between the targets. So as you can see, we have like a set of the trajectory, map it with the MLP to the higher dimension, use the LSTM to encode each of them, one feature representation, use that as a node of the feature node, graph nodes, and then use the graph attention network to learn a joint representation between them, and then concat it with their local information in order to predict the future of each target. So that was one of the contribution we used. The another contribution was the again has the like a GAN is able to predict a single modal distribution and has a mode cloth problem. We rely on the like a cycle GAN type of things. It's called bicycle GAN in order to deal with the like a problem of this mode collapse and multimodal generation. We believe that future prediction is not single modal. We can have a very diverse route which all is equally correct, or might be kind of like a some of them could be less risk than the others, but look like the prediction is not a single modal distribution, is a multimodal distribution. So we rely on the bicycle GAN to formulate this problem. We had other novelty, like we use some global discriminator, because previously everything just when we use the discriminator, we look at the trajectory of each target in future and try to say is a real or fake. But we could really look at the entire of the scenario together, means all target together and the image together in order to find out if this scenario makes sense. All right, so far I explained how, if we have a trajectory so far, how we can make this forecasting end to end. The main problem is like a majority of the works in the committee try to predict the human motion in future, like a single location, means the whole body is mapped into the single location in order to say what is like how would be the future of the object. But we are not interested only on the entire of the body motion, also very more detailed information about the body joints and how the human moves in the environment. So we are trying to model the like a body posture and the motion jointly and try to predict it in the future. And this is the paper we had again with the Stanford team, and in that paper we try to do the human skeleton pose forecasting, but not in the ways that currently formulated in the community, which try to just care about this, like most of the paper care about the like a human body posture without their like their absolute like the global motion. Means it's when a person is running, it's just try to say how we can predict the running behavior without really modeling the displacement. And it's a very important, these two problems to be modeled jointly for, again, for navigation purpose, because we want to know what a person does and where it goes in the future together. So one of the contributions in this paper is to try to model, predict the global motion and then joint pose forecasting together. Another idea in this paper was we use, excuse me. Yep. Again, sorry for the problem. It's in the video crash after a while. Yep. Another thing we try to formulate in this paper is to say, like, if the pose forecasting cannot be independent from the context, scene context, and the other people in the scene, posture of the other people in the scene. So we try to have a model to learn a joint representation between a skeleton of the people in the scene, model encode this scene context into the like a feature representation before decoding it. And we also provide like a way to do a joint learning between motion and pose. We tried on the set of the data, so like a pose track, and we compare it against lots of the baseline, including the baseline, which try to learn each of the like a motion independently from pose forecasting. And we show, okay, if we have like a scene context, social context, and then we model the motion and join together, we have like we can improve the result. Yep, here is the one of the visualization, just show if we have a joint learning, social and context, and if we have like just human skeleton pose separately and the motion model, social, like a social game separately, we can better learn when we do joint learning, when we incorporate the social and context information. Yep. Yep. Now we have like a detect human, we track them, we can predict their motion and joint behavior in future. All is to the very last stage now, given all of them, how we can understand what does human do in the environment. Means and not only considering the individual behavior, but also look at more collective behavior of a human in the environment. Means we had another work from my group, is from Adelaide, try to provide a way to model the human
existing works for.
Again, I apologize for the problem. It seems it has a voice, and I'm trying to explain it over the video. Yep, this work will appear in this like a ECCV this year, and is about a human understanding human activity is not just classification of the video or even detecting everyone in the scene and then try to understand the activity every individual does. Is about more about what the people in the environment does together. Means a scene is a consist of the a group of people. Some people are individual, some people are together, and then the goal is to find out how we can learn who is with whom from directly from the video or from point cloud, and what they are doing together. Means understanding, find out each individual in the scenes, and then find out okay, who's interacting with whom, and how we can create a subgroups in the sense of who is interacting, and then what everyone within the group try to do, and how we can have a model, end-to-end model to deal with this problem. For this paper, we provide a data set which has this annotation to kind of cluster the people into the subgroup. And the main idea behind it is to say, if you have a video clip and then we extract some feature like a 3D feature, like i3D, then how we can extract the feature, how we can detect every individual, how we can extract the feature from individual and their local information, like a local pose. And the main idea is to say, if we have people in the scene, we can model it again as a graph and try to learn the people who are together to be closer together. Means learn edge relationship between them, which if the people are together, the edge should be stronger. And then when we have that, during the test time, we can run a graph clustering to partition the people. And given like a partition of the people in the scene, then we can look at in each individual nodes in that, and also the partition graph, which is a subgroup, in order to find out what's the individual action, what's the social action within that group. In this talk, I mainly discuss about the perception module we try to do to understand the human behavior, and there is still lots of things is remaining to be done, especially about the multi-object tracking. Still, there is the blocks stop us to make the full system end to end. But another bottleneck we will have, assuming even we can formulate the entire of the problem end to end, is we don't have a unified data set which can have all of those annotation in order to train all of them together. Means we have for the detection, we have a Pascal VOC or COCO data set. Then for multi-object tracking, we have mode challenge. And then for pose, we have pose track. And for activity, we have different data sets. We cannot really train all of them in the different data set. If we want to really train things together in end-to-end, we need the data set which has the like a unified annotation. Again, we try to provide that data set. Actually, we recently released a data set. It's called from the robot platform, which is the Jack Robot, which is a robot project in SVL, Stanford Vision Learning Lab. And this robot is called Jack Robot. This robot is equipped with the modern sensor, and we try to go into indoor and outdoor environment, collect lots of data, and then start annotating for the relevant task. The data we captured so far is over 60,000 frames, about 67 minutes of sensor data captured from the different sensor. This robot equipped with like a LiDAR sensor, 2 LiDAR sensor on the top and the bottom to make the 360 LiDAR scan. It has the 5 stereo cylindrical 5 camera RGB sensor, which we have the view of each of these cameras, plus we can create a stitch panoramic view of the entire scene. We have an IMU sensor, we have a one channel LiDAR at the back, and we have a 360 fisheye camera at the top. audio signal, encoder value from the robot wheels, and GPS value. So everything we might need for as a sensor measurement for a robot. And the images from the 5 stereo camera, as I said, we have 5 stereo camera, and then we can stitch it to create the 360 panoramic image. And then along with the point cloud LiDAR, we can have a 360 view of the image in 2D and 3D. And we have the registration information between these two sensors to this, and we can color the point cloud or project back the point cloud to the image. So the data has mainly 3 phases of annotation. The first phase of annotation is finished last year. And then that's about the 2.3 million high quality 2D bounding boxes annotation of all of the all person in the each individual camera as well as panoramic view. 1.8 million high quality 3D oriented 3D box in the LiDAR data, and all 3D, most of the 3D has associated 2D in the but we have more 2D bounding boxes because there is more people visible in the image and there is no point cloud associated to that. As I said, we have association between 2D, 3D bounding boxes. We have more than 3,500 time consistent trajectory, which make it one of the biggest person tracking data sets. And we have like around 4 benchmark for 2D tracking, 2D detection, and 3D detection and 3D tracking for pedestrian or person. Here is some of the video of how the data look like. As you can see, it's a very high quality 2D and 3D bounding boxes, and it's very different from any data set out there. Even like a self-driving car data set is captured in the highway now indoor, and they don't have such a high temporal resolution annotation, and this data is very useful to analyze the human behavior in indoor and outdoor environment, and the robot can be very close to the human. We capture the data when the robot is not moving or moving, and like in this case, the robot can move. And as I said, it's a variety of the indoor and outdoor environment, and that makes it very, very unique data set. This is the first phase, and then this second phase almost is finished as well, and we have the annotation of the human activity and action and the grouping, social grouping, which is the who is with whom in that environment, and which that can be used also for the task I mentioned. So having the 2D and 3D detection and the activity, and for the third phase, we will try to annotate human skeleton pose as a joint or densely in 2D and 3D. And having all of them, then we have all of the annotation for all of the mission modules. Yep, if you want to have a look or submit to our benchmark, as I said, is another 2D pedestrian detection and tracking, like a mode challenge as well. You can use it, but it has also 3D data. It has a stereo camera. So if you are interested to have a closer look into the data, I provide the QR code for the benchmarking data. We upload the paper, which is under review with the TPAMI, and there is a page for the Jack Robot projects. All right, thanks. That would be the end of my technical presentation. Okay, sorry, I'm a bit sick, and sorry, middle of my presentation also I had the same problem. Yeah, now it's a question. Let me. Okay. Oh yeah, there's lots of question.
Can you hear me, Hamid?
Yes, I can.
All right. Thank you very much for the presentation. I know that you've been feeling sick lately. but thanks for making it to the presentation. Really appreciate it. So I'll try to read out the questions that the audience has popped up.
Before, can I
yes.
redo the slides in the case of, can I replay? Oh, I think
Sure.
I can.
So you should be able to share your slides.
Yes. Okay. I just in the case yeah, please go ahead.
So the first question is,
we could.
Yeah.
Important. I think they can unmute and directly ask. Like understand what's our union of A and B divided by C. It means if two shapes actually, not the better detectors, I mean end-to-end object detection with no post-processing or heuristic, like a non-maximum suppression. By this paper is about how we can just fuse. Regarding the first question, actually experiment under a robot itself directly when the robot between human in order to evaluate how under a robot itself directly when the robot I didn't follow exactly. What do you mean? You can just decide about the maximum number of targets. And let me just go to how the motion target moves. And then when H here is the hidden memory. Maybe it's easier to unmute if you can speak, because I believe you can do that. You can unmute and directly ask.
So Hamid, do you have my voice?
Sorry?
Can you hear me now?
Yes, I can.
I think I was interrupted for a few seconds. Okay, so so the first question is, Eloy has asked, I have a question about occlusion. How can we deal with occlusion?
Okay. I thought the first question is what I can see. Okay, let's go based on occlusion. Okay, occlusion is occlusion is when we don't receive any detection but the target is still alive. Means yes. Okay, thank you. Yeah, the target is still alive and we don't want to terminate the target. That's equivalent when we have a misdetection. Do not let that binary variable to be dropped. Okay, so during the training, actually we have the cases which the tracker does not have any good detection, but still we are learning, forcing the network to be alive. And there is a lots of reason for that. For example, the model is try to find the mapping if the target, for example, is the middle of scene, assuming in the like a vision application, and there is no response. I still believe the target is alive. It learns to predict, even if you don't have a good detection or any detection correspond to that. Do not terminate it. A termination happens, for example, in the boundary of the images. So the model should be able to learn the differences between when is there really occlusion and when is a real termination. And since is the RNN module and is a long-term memory is there, actually, you are expecting the model to see a longer horizon in order to decide is occlusion or is a termination. Make sense?
Okay. So moving on to the next question. There was a question about, I think there's two parts to the question. So that's the first one. So are all learnable parameters shared in one block? And I think the question was followed by saying that, I mean, all of the W parameters are one parameter that apply to different inputs.
Okay, it's a bit hard, the question for me to follow.
So I think this was in your end-to-end tracking. Yes, the one that you mentioned is a true end-to-end tracking module.
Yep.
With the LSTMs.
I assume the one thing we say is the shareable parameters is across all of the target. The RNN modules for prediction and update is the same for every target. We just have a duplication of that one. But I'm not sure what do you mean all of the shareable is in the one block or not. The RNN we design is a very specific RNN, has a set of the parameters, and the input to that is a one state of the target, and output is the predicted state, and then if the target is alive or not. We partition the parts to be prediction update, by intuitively they are all one RNN block. Makes sense?
Okay, so I'm just going to maybe change the question a little bit. So by saying that, for example, in your SOFI framework, where you have modules for different agents, you can have variable number of agents, right? So do you have one encoder module shared between different ages and different people, or do you have one encoder for each specific person?
Is it a question about trajectory forecasting, or is it for end-to-end multi-object tracking?
Yes, so this one is with SOFI.
For the SOFI, the RNN used to encode the past history is the same RNN, is a shared RNN between them, and then you can deal with any variable size tracking. It's the idea of the inputting a set of tracks, and then it should be not a problem to have a variable size input.
Okay, so moving on to the next question, we've got a question from Rahim. So in ECCV, can you please give us, so in your basically social activity understanding paper, can you please give us more details on graph partitioning module and how it works?
As I said, during the training, we try to just make the connection between the nodes stronger by a loss, like a cross entropy loss. Forcing during the training, we know who's with whom, and we try to make them the graph for the edge between those nodes of the graph to be stronger. I mean, during the training, we don't have a partitioning. And when we have the actually during training, we pulled from the ground truth partition to predict the group activity. But during inference time, the truth membership or like a social interaction is not known. So we input the graph fully connected and output a graph with the different edge weights, and then we give this one to the, like a spectral clustering techniques to partition the graph into some set of connected components, and those connected components, it becomes our subgroup, and we try to estimate activity within each of those subgroups. Make sense?
Okay, so essentially the graph partitioning module is being used during inference, right? To basically create partitions of the connections between different individuals. Okay, so moving on to the next question, we have a question from Badia. So he wants to know if you use deep graph neural networks for learning the relationships in group activity recognition.
Yeah, I think we use a specific graph network. It's called graph attention neural network, which tries to learn the attention in order to embed the feature for each graph node. It has a self-attention modules as well. Yes, and we try to learn the relationship. I don't call it group activity. We tried on the group activity test. Group activity means we assuming all of the people in the scene contributing to the single activity, but the difference here, we assuming the people in the scene can be actually partitioned into the subgroups, and subgroups can be like a subset of the people in the scene. Some people can be like an individual with no one, and some people might have someone to accompany. So that's what we call the social grouping actually, and that problem is for the first time we discuss how we can use the deep neural network to do that.
Okay, I think we don't have any more questions, but I'm just going to ask a question myself. So with the paper that you mentioned on introducing a new metric for object detection or different visual tasks, so the generalized intersection over union. So is this metric right now replacing the de facto IOU, or is it being used as a complement to that one? Or is there like any benefits to using IOU anymore?
Okay, good question actually. So far within the 1 year, the community it actually see it more as a loss than metric. Still, but I can see there was many cases you try to solve a matching between two set of shape, which they might not necessarily overlap, and then they end up to like a real IU become like a failure cases, and actually for the long term the GIU should be a better alternative because it has the same exactly identical property of the IU. It's a very highly correlated by IU when there is an intersection, but when there is no intersection, it still give you a response, while the IU doesn't give you any response. It means always zero. It creates a plateau. Yeah, expectation is to for the long term. It's seen as also alternative metrics, not. But just to add, IU is first defined in the set community. It's not necessarily okay. Shape is a infinite set, but you can have a finite set as well, and you can calculate intersection between set divided by union. But this generalized one is only applicable for the shape because the meaning of the convex hull and the tightest convex hull, it does not have a meaning if you don't have a special sets. If it is a general sets, it doesn't have it. So yes, for shapes could be a better solution, and IU is not longer like a good metric because we have a better metric to use.
Okay. So there is one more question. Yes, so there we go. So it says your loss function on partitioning is encouraged to be less in one cluster, right? It also encouraging between groups distance. I see a challenge to optimize the number of clusters.
Partition is encouraged to be less. Actually, we don't actually. There is a like an upcoming paper. We try to incorporate the glove actually clustering technique inside the learning module. But this is not in during training. This existing technique does not care about the clustering. The only thing it's encouraged to do is a pairwise relationship between means. We don't do any partitioning during training. What we try to do actually, if we know these three persons is together, we try to make edge connection between each of the pair stronger. That's all. We don't really try to ensure that all like they are partitioned together, and that's one of the weakness we are aware. Means during the training we try to make the edges between them stronger with the hope of when we do graph clustering they become one connected component. But because a spectral clustering was not the part of the learning, we couldn't incorporate it. But we have upcoming work which we already tested the idea of how we can have the clustering and partition graph clustering directly as a loss to backpropagate.
Okay, so Hamid, just to reshape the question a little bit, so are you in your current work assuming that the number of clusters is known beforehand, or are you assuming that the number of clusters K is to be inferred from the data?
I think that's a bit specific to be asked from the student. I assuming the graph clustering using a spectral clustering has a technique to estimate. There is a heuristic to estimate the number of the cluster. Is a bit, for example, find the maximum maximum job between eigenvalue of the and then I think I'm not sure, maybe it should be double asked from the first author of the paper. We rely on these to estimate the number of cluster, or maybe we use we assume that's known already and we use the truth one. I'm not sure which one really is implemented.
Okay. So Hamid, what is the next step? So I can see that you're trying to make object detection, target tracking, approach this problem as end-to-end problems with deep neural networks. So where do you see yourself as the next step on these projects?
Okay, one thing is to have try to get rid of heuristic and then make the some of the components which doesn't let us to bring like a high-level perception module to be end-to-end and make them end-to-end. But that's just make the perception end-to-end. One of the interesting topics is to have the perception in loop. When you have a planning and the perception together, when you do perception, then perception decide about your planning. When you do planning, you have a new environment. You can use it actually to adapt your perception based on and so keep everything in the loop and then make everything end to end is the ultimate goal. Means do the robot planning and perception and make them on the loop such that we can improve the perception by feedback we get from the environment as we plan as well. So that would be a nice way to go.
Okay, so I appreciate, okay, one more question. I think one more question just popped up now.
I think you need possibly to contact the first author for those questions about that.
So it would be good if you can share the links to the papers afterwards, so you can directly read the papers about the implementation details to optimize the number of flops, for example. All right, so Hamid, I've been informed that you have an announcement to make. So I'll just ask the audience to stay with us, and I think we'll have a short video to be played. Yeah, good news for everyone. So thank you very much. I appreciate the talk and your time.
Thank you. Okay, that's a very quickly just for those who are interested to continue their PhD and thinking about the coming overseas to do a PhD in the good institute. Again, I recently joined Monash University as a assistant professor. And I'm trying to build my own team, which it would be like closely working with the many universities inside Australia, and also has a very good connection with the prestigious university like ETH Zurich, TUM Munich, and more importantly, Stanford University. I just wanted to a bit like advertise my group and for the students who are interested and has a very outstanding CV. If they want, please try to send me an email, include your resume. Just a bit about Monash University. One thing, the group I have, it's located in the Faculty of Information Technology at Monash University, Melbourne, Australia. Monash is one of the G8 universities, the top 8 university in Australia, and it has only university has a faculty for information technology. And my lab will be located in the Department of Data Science and AI. And as I said, the Monash is one of the second biggest university in Melbourne and one of the top 8 university in Australia. For those who are interested in ranking, this is the QS, is one of the prestigious and a very well-known ranking, university ranking website, which this information is for 2021. Monash University is between the top 6 university in Australia and is ranked between top 55 university in the world. Specifically, even if you care about the computer science and information system, Monash is a top 4 university in Australia. About the Melbourne, for those who cares about where they wanted to live, also is very important. Melbourne has ranked as the most livable city for 7 years in a row, and the last 2 years was the second best city in the world. So it's a very beautiful city with high quality of life. and to mention it generally, Australia is like that. It means a student too much care about going to the Europe and US. But if you want a good place with which you can thinking about your future, it's an English language country, can accept the immigrant, very beautiful, has a great weather, it's not like a Canada, and has a very good university, and you want to enjoy your life and do your career in the future, consider Australia. If you are interested, please contact me. I provide the QR code for my Twitter, LinkedIn, and Google Scholar. You can find my email here. And please attach your CV and include your transcript. I have a very limited funding for the next couple of months, and we are looking into get the very outstanding PhD student. As I said, the student work with me will have an opportunity to be connected also to the ETH, TUM, and the Stanford University lab. They might have an opportunity to visit the Stanford Vision Learning Lab directed with Silvio Savars and Fefe. Depends on their performance, and maybe could potentially apply for a postdoc there as well. All right, thanks. Bye.
Everyone for joining us for this session. That's it. That will be it for this session, and then we'll see you soon with Snoop Talk. Till then, bye for now.